Hello everyone, my name is Dale Mudd and I'm a grad student here in the astronomy department at OSU. I'm here today to discuss with you briefly my recent paper that appeared in the archive, Discovery of a Redshift 0.65 Post-Starburst BAL Quasar in the DES Supernova Fields. Now, that's a bit of a mouthful, so I'll begin by unpacking that statement for you just a little bit. DES stands for the Dark Energy Survey. It's a large collaboration of dozens of institutions and hundreds of scientists across the globe working together to better understand the evolution and expansion of the universe. This is tackled through several means, such as using supernovae and baryon acoustic oscillations as cosmic rulers, as well as gravitational lensing and galaxy clustering as cosmic scales. While the survey covers over 5,000 square degrees, the supernova fields are a smaller subset of 30 square degrees that are visited repeatedly to try and discover these bright transient objects. The AusDes, or Australian DES program, complements the supernova fields by taking spectra of the host galaxies of these supernovae to better determine their redshifts. Several other types of objects are also being monitored in the supernova fields via DES and AusDes data. One of these is quasars, or actively accreting supermassive black holes to the centers of distant galaxies. Now, these black holes are too far away and too small to be resolved with even the best of telescopes today, but we can learn more about them through their emission properties and its variability over time. As repeated spectra are being taken of these quasars to track their variability, we discovered one that had a unique combination of properties, as shown in this stacked 160-minute exposure. On the right, we see a partial broad emission bump from H-beta arising from the broadline region around the quasar. The broadline region is typically of order a few light days to weeks in radius from the central black hole. Now, the central portion of the spectrum is dominated by the host galaxy instead of the quasar, as we see stellar absorption features of the higher order Balmer transitions for hydrogen, followed by the Balmer break. These features suggest that this galaxy has undergone recent, but not current, star formation. As a star's lifetime is inversely related to its luminosity and mass, we expect galaxy spectra from regions undergoing present star formation to be dominated by the youngest and hottest stars. The features seen here are more prominent in A stars rather than their more massive cousins, the OMB stars, and indicate the galaxy is likely in a post-starburst state where the somewhat less massive but longer-lived stars emit most of the light. As we move bluer to the left, we see more broad emission lines arising from regions around the quasar, with iron-2, magnesium-2, and helium-1. More striking, though, are the large absorption troughs seen in between these emission bumps. This quasar appears to have absorption from iron along with magnesium, making it a rare iron lowball, or low ionization, BAL quasar. Fewer still BALs have been seen to have broad Balmer absorption, which this object seems to have as well. The exact nature of these iron lowball quasars is still a bit of a mystery. One model proposes they are young quasars transitioning from a dusty, obscured phase into an unobscured phase via strong winds that are blowing apart this enshrouding material. Another model proposes there is a blast wave that emanates from the quasar and expands outwards until it impacts a dense cloud of material along our line of sight, disrupting the cloud and then carrying it along with the blast wave. Both of these scenarios have material that is moving at high velocities towards the observer, which would then create these large blue-shifted absorption troughs that we see in these iron lowball spectra. We inspect the DES images and find that there are 3 nearby galaxies, here shown with bold X's over them, that have photometric redshifts consistent with the BAL quasar. This hints that it is undergoing some sort of merger activity that could possibly fuel star formation and quasar activity. By modeling the portion of the spectrum dominated by the stellar light with population synthesis predictions, we can get an estimate of how long ago the starburst ended. Our best fit model is primarily comprised of a 40 megayear-old population, shown in dark blue, and a quasar template, shown in cyan. The regions in gray are masked out because they correspond to areas of the spectrum believed to be contaminated by the broad absorption lines. There's also a small contribution from an older stellar population between 10 and 13 gigayears old. If we make the strong assumption that the star formation ended when the quasar turned on and began moving away material that could otherwise form new stars, this gives us a unique limit on the age of a quasar. Quasars are believed to be active for on the order of 10 to 100 megayears. So if this quasar is 40 megayears old, it's comparable to estimates for the total time it should be on. This is somewhat at odds with the young quasar scenario presented earlier, but acceptable by the blast wave scenario, which gives us some hints as to the formation mechanism for this particular iron lowball quasar. We will continue to monitor this fascinating object to learn more about both its host galaxy and absorber properties. If you'd like to learn more, please see my paper that was posted on the archive at the link below. Thanks again for watching.